Yeah, I will start the presentation with giving a quick outline on what's on the agenda today. So we'll start with an introduction in terms of some words about myself and also about the project and what are the objectives for today. So similar to José's and Roberto's presentation yesterday, I will give an outline on what do we want to do today and what is the core audience of this talk. Then we will continue with an update about status quo of existing methods in the industry today and give a motivation, why do we need powerful reliability models of medium voltage cables. Then, and I think this is particularly relevant for also some of the people joining online, we will go a bit more in detail into the fundamentals required for such a development of the medium voltage cables in terms of a little bit of system reliability theory, but also two use case presentations of applications which are in use today. Then after the break, we'll shift the focus towards my PhD project, and we'll talk about why it is an interesting research field to leverage artificial intelligence in contrast to the use of traditional reliability models. So we'll talk about opportunities, but we will also talk about implementation challenges, mainly related to the data collection part needed for such models. But let's start with the introduction. So to set the stage, some very quick words about myself. So I'm originally from Germany, and before starting the InnoCyPES project, I worked as an engineer in the innovation department of a DSO in Germany. But also did my master thesis in collaboration with the TSO in Germany. So my focus is on medium and low voltage grid assets, and in particular, how can we make them digital and smart? And that's why I also continued my journey in this domain, and joined Green Power Denmark and DTU for my PhD on the topic of condition monitoring and predictive maintenance of distribution grids. But to put this into the bigger picture, so this slide or a similar slide we have already seen in a couple of other presentations during this week. We have a lot of interesting PhD topics from different domains in the energy field, and also structured after the data workflow in terms of acquisition management, application, and symbiosis and planning. And you can see that I'm located in the middle, so purely focusing on the distribution grid domain, with the focus of building an application, so in work package 3, and from the disciplines of information technology, energy systems engineering, and also a relation to social economics and policy. But before we really start with the content, what is the main idea or the initial motivation for my project? So in reality, we see that the rollout of reliability models is quite limited in industry, but at the same time, we see a huge potential because in the past, there has been an extensive collection of fault records in Denmark, but also, of course, also in other countries in Europe. And the data availability of relevant features such as weather observation, GIS data, or digging payments is getting better and better, also due to digitalization efforts in other industries, branches. So that's why we can formulate this opportunity in saying, let's build a reliability model and analyze data correlations. And then I will now also provide more background why this is relevant and why this is actually that much needed. But one thing I wanted to emphasize, also after some discussions we had with some external participants yesterday, of course, my project is not seen as one isolated project, but it has a lot of interactions with the topics we heard during the week, and we will also heard during the day today. So for example, from the information and measurement domain, we heard yesterday in the afternoon Lunozzo's presentation about data management. And because we really need a lot of data for build these reliability models. So that's why also we can profit from the learning and from the knowledge collected in Lunozzo's project. But the same is true for for example, Gutai's project, where we'll learn today about data enrichment techniques and modeling of smart meter. Of course, also the presentation from Jose and Roberto yesterday in terms of cost-benefit analysis, regulation, policy making is highly relevant. Yeah, and there are much more topics and links to the projects. And I hope that after this presentation, also for the external audience, it will become a bit clearer how these projects are connected. So now let's take one step back and let's look at the slide at what is actually on the agenda today. So what do we want to learn from this presentation? So I would be very happy if after my talk, you have a basic understanding of the relevance of reliability assessment in distribution grid asset management, and you of course also are aware of what does it mean, distribution asset management. I also want you to get familiar with some real-world applications so that you have a basic understanding on what is the status quo, so what is actually used in industry today, and why do we want to challenge this? Why do we want to go one step? Yeah, and then if time allows, maybe we'll get also some hands-on experience on some available methods and toolboxes to check out how would we actually build these models or what do we need for this. We can have a discussion about that. And as I already said, better understand the interactions between my and the other project. Yeah, so now there are some slides which probably most of you are familiar of, but I think it's still a good idea to remember why we are doing all of this. Right? So when we look at in this particular case Denmark, because that's also where I'm based, yeah, we can observe that in the last decades there has been a huge shift towards decentralization, and decentralization means also that the role of the distribution grids increased drastically or radical. So in the distribution grid, this change is really drastic. And not only from the production side, but also from the consumption side, we see radical changes. So one trend is, of course, the electrification of the mobility sector. But another trend is also that the heating sector has also started to electrify. These numbers are all for Denmark, but we can see that the growth is exponential, and this actually, of course, in the end, will do something to the electricity consumption and also to the infrastructure needs in the distribution grid in Denmark. So that's why when we now look at some prognosis here made from my colleagues at Green Power Denmark, we can see that the electricity consumption is expected to double by 2030, which is also, when we look back to the development, how it has been in recent years, an extreme change. And yeah, grids, they have been not designed for this, right? So the medium voltage networks, the substations, the low voltage networks, they have not been designed for this, because this drastic trend has not been anticipated or from the grid planners 20 years or 30 years ago. And This results in the fact that we need to have investments. We need to modernize our grid. That's a fact. And in some countries, for example, in the Netherlands, we already see today like highly congested medium voltage networks, which which already today cause problems in the operation. So it's not something we need to react tomorrow, but it's something we really need to react today. And one study also made by my colleagues at Green Power Denmark shows that we actually need a lot of investments to cope with these challenges, but also with natural modernization of the distribution networks. Because like in your own house, there always needs to be some modernization or replacement. Yes, and if you're interested to dive more in depth into these analysis, I provided the link to one of the studies where there actually has been an investigation on what are the actual investment needs in the distribution grid in Denmark. So, and another comment I want to say also to the audience here physically, but also online, in case that there are any questions, please interrupt me and we can take them right away, but we will also have some time later to discuss. Thanks, Anne.
Thank you, Conrad. I'm just curious, what will happen if the investments are not made? Thank you. What will happen? I mean, rise, but
yeah, so I would refer in that case to this triangle of reliability. So that means that consumption or delivery 99.99999 of the time. So at the moment, in Denmark and also other countries in Germany are very good, like have very, very high numbers in this indicating this system reliability. But one effect of such the lack of investments could be that these numbers decrease, so that they're basically just happening more failures, which lead to there's of course not a blackout on a system level, what we maybe have in mind from a TSO grid, right? Where then like northern Italy is dark, but in a smaller scale, right? So that more customers and end customer level would experience downtime and outages. That could be another problem, which is related to installation of or connection of renewable energies, right? So if we say we're not upgrading our grid, then someone who wants to connect a solar park has challenges in getting a fast connection permit. So that could be another consequence, but it's multifold. Also, maybe just to give a very high level. So now that we've set the stage for why do we need this, I would like to continue with some words about asset management of medium voltage cables, because this is the domain which also exists almost after the the start of electrical engineering and operation of power systems. So and this domain focused on exactly this. So we have these two objectives. So we want to deliver a reliable, we want to deliver in a reliable manner electricity to the end users, but we also want to make it cost efficient, right? So it's not because one solution, and some people could also argue that sometimes it's the case in Denmark and in other countries in Europe. We want to make it as efficiently as possible. So the solution is not that we put as much as grid infrastructure as we can and spend a lot of money, but we need to make it in a cost efficient manner. And that's why we need to have strategies for that. So we need to have a plan. How do we upgrade our assets? When do we upgrade our assets? How much money do we invest in certain components what are the critical components. And we also, now in modern terms, because our resources are extremely limited, we also need to sometimes say, let's postpone investments because we just cannot do them at the moment. So we just only want to prioritize the investments which are needed today. And another concept, this maybe goes also a bit in the question Annie just mentioned. What if we could increase our utilization of the assets we have in place? But this, of course, also requires more knowledge and powerful methodologies to evaluate, can we take this asset more to its limits? Yeah, and here on the picture, you can see it's obviously not a medium voltage cable, but it's a distribution secondary substation. So this is just to show that, there are a lot of components which we need to look at in this particular domain. So to sum up, we need to know why and when the individuals or common components are failing. So that would be ideal, right? When we say, okay, I know this component will fail in 2 months or it will fail in 3 years, then I can really make an informed decision and because then I can predict the conditions, I can predict future failures, I can adapt the operation, and I can also prioritize my investment strategies. Okay, but now when we say we have a lot of these components in the network, still the question is, what component do we start with? And as a DSO, of course, you don't have the luxury to select, but in a PhD project, you have the luxury to select because you need to prioritize and you need to go into deep in one specific topic. And that's what we did. So we selected the medium voltage cable systems as the most relevant part of the story for us. And we have several reasons for that, and I want to share them with you now. So first reason is that we have indexes that measure the downtime of components from a system level. So that we say, what is the system average interruption duration time of all the components we have in the network, so on an aggregated level. And that enables us to indicate some of the relevance. And in medium voltage cable in Denmark, we can see that 45% of these indexes are originating from cable systems. And we can look at another indicator, which is called the System Average Interruption Frequency Index. So this just counts the number of interruptions in the system. And there it's pretty similar. So this gives a first indication that let's look at this component category because it actually contributes a lot to the things we want to avoid. Yeah, and there are other reasons, and I borrowed these 2 pictures from one of a good colleague of mine at Green Power Denmark. But another problem in medium voltage system, and I would also call it like a problem, is that we have different technology sets. So we have on the one hand, we have modern XLP cables, and I also will show you the differences in a minute. But on the other hand, we also have PLC cables, so paper insulated copper cables, which represent have been installed a long time ago in the networks. So it's also have already stopped to be implemented, but still present in the network. And there we can, from a higher level point of view, already see increased failure rates. So that means that the components from a natural aging process arrive to a point where the probability that they fail increases. And that, of course, also shows us that we need to do something. And of course, the first step of the DSOs is to define replacement strategies for this component type. But there we still have the same problem, right? Even if we say we want to get this component out of the network, we still need to prioritize what individual component from this specific technology should be replaced first. Yeah, and now some pictures also to give you a gut feeling of like, what are we even talking about? And if you're interested in this, I can also point you to some more detailed pictures, because I also realized that the next slide, it's actually not the cable type that is used in Denmark, so it's a different but similar type. But I probably you will. It's also hard to spot the differences. But one important thing you can see here is that the insulation, so the material around the core, is paper. So and it's impregnated with oil. So that's why it's often referred to like that is oil is also often connected to this cable. But the core difference lies here in the insulation and also in the covering of the cable. And this is the this older technology I just mentioned before, which is still present in a lot of networks in Europe, and also in particular in Denmark. And if we look now to the more modern option, let's say, so it's probably, if you've heard about that, it's also more like what we have in mind of classical cables. So it's like cross-linked polyethylene insulated cables. And yeah, here it's for example number 4. There you can see that we have instead of the paper, we have different insulation type, which also reasons better performance in terms of reliability. So we can just see it also as an a technology improvement from this point of view. But before starting to build reliability models, it's of course very relevant to ask the question, yeah, what is actually driving aging? What is actually driving that the cable fails or that the cable degrades? And for this, I presented the main drivers, also taken from previous literature. So, and they are often categorized in 4 over categories. So a cable can age due to thermal reasons. It can age due to electrical stress, environmental stress, and mechanical stress. And then we can, of course, go more in depth. We can say, okay, what are thermal drivers? So extreme temperatures could be a driver. For example, in Paris in the summertime, there are very interesting studies that the city is heating. So like the ground gets warm, and that for medium voltage cables is very bad. So in very hot summer days in Paris, the colleagues from InnoCyPES have a lot of work to do, because then the failure frequencies increase. But also temperature cycling. So when it goes up, down, this can lead to stress. And you probably you will already notice that these factors here, they are also interconnected, right? So when we have some electrical stress, so for example, we have a higher short circuit current, then it will lead to some temperature issues, or and if it's then also collected to water, then the environmental factor comes into the picture. But also from the environmental picture perspective, there are a lot of different options. It's related to the soils, chemicals. There are some studies that because of in agriculture, what type of chemicals used, that this might interact. So the topic is really broad, but the main message I also want to, or a main message I want to give to you is, yeah, we have a lot of drivers affecting this aging, but it's also something where there is a relatively clear picture, a relatively clear understanding about. So we also know that when we bend the cable too much, then this will cause problems in the long term. So that's the main message I want to give to you here. Yeah, and then I found it, I thought it could be a good idea to also show some of the damaged cables, because it's always a bit funny for me to see, like, for example, how a medium voltage cable looks like after, in this case, it was a short circuit burn down, right? So looks more like a bone, or so it doesn't really look like a cable anymore. And another thing which I want to point out, of course, we talked about aging factors now, but there is this step in the middle, like aging mechanisms. So it's like a process of where different factors contribute to each other, which is also then not always very clear how then the effect in the end occurred, right? So it's not that we can say, okay, we had one high temperature and now then we have this problem. So it's more complex, and that's also why it's so difficult to model the aging process. Yeah, and here this is of course now 110 kV. So in many countries it's not distribution grid anymore. But this is another phenomenon. This is a bit more or less academic maybe, but here just a digging company digged into a cable, and this actually also made a big share of the cable failures. And then when the insulation is damaged, then of course some other effects, some electrical faults. Yeah. And here I have, similar to the previous topic, I have some references for further literature you can check out. And in particular regarding the aging mechanisms, because there are pretty nice overviews which lists all the different factors. Any questions so far, or?
Thank you, Conrad. So yeah, I wanted to ask, because you showed very well, very comprehensively all the factors that can affect the cable failure. But since you know that we are also modeling and use very high level numbers estimations there, and I was using loading or also if the cable is underground or not. But I would like to know if, for example, would you include what could be the 3, 4, 5 most relevant parameters in terms of, would it be loading, would it be temperature, would it be underground or overhead? Thank you.
Thank you very much for this question, Jose, because I think it's spot on. So of course we have certain indication on this, but it's actually also something we would like to find out in our project, because the assumption is that in different geographical areas, maybe also these different aging factors have a different relevance, right? So on a very higher level, it's already difficult to evaluate, which is interesting. Of course, maybe I will talk later a bit more about the failure reports. And there are, of course, failure reasons also related, where we could, for example, say, okay, this failure originated from digging activity. In this case, of course, it's clear. But it's from a historical point of view, it's very hard to say, okay, this failure was due to overloading. But this is something where we would like to, would like to have more knowledge about it. So of course we could, if we go back, we could take these features and probably structure them after expected relevance, right? So if there is a short circuit now I need to be careful not saying something wrong, but for example, if there is a very intense bending or something like that, then it's obvious that this probably will have a bigger effect. But to my knowledge, this clear categorization is unfortunately not possible, and it's something where in our work we want to gain more knowledge, and we hope also that these new methods will help us to gain more knowledge. Okay, maybe not the most satisfying answer, but I will continue. Okay, so yeah, next chapter. Yeah, before while making this presentation, and also because in this summer school we target also external people, I thought it is an interesting idea to talk a little bit about fundamentals of system reliability theory. So we have the same perspective some basic techniques, and so that we not directly dive into machine learning and AI, and this will solve all the problems, but that we just say, okay, what is the theory behind? And the interesting part in this system reliability theory, it is actually a very well established and very old theory. And of course, there are a lot of literature, and I will actually focus on the book on the right-hand side. So, and this is also the oldest book. So I think this is like really basic what we are looking at now. So, but what is meant with reliability? Maybe that's the first thing to start with. So, and the ISC standard defines it. It's the ability of an item, can be anything, or a system or a cable, to perform a required function. In our case, for example, electricity distribution under certain given environmental operational conditions. In our case, that could be where the cable is placed, how it is operated, for a specific period of time. And then, in order to measure how well this ability is kept, we have some reliability measures. This could be, for example, how long does it take in average until a cable fails? It could also be, when we look from a system perspective, how many units of the same category are failing. So that would refer then more to a failure rate. And we have a lot of engineers in the room. So another nice concept, of course, is the probability, right? So that we have a certain period of time. What is the probability that this item will fail? And then we can also switch that around, and we can say, like, what is the probability that this item is able to fulfill the function over time? I hope you can you see this? It's not very strong, these lines here, but these are some very basic mathematical formulations, which are very common in reliability theory. So the first is the probability density function. And because it's a density function, is it always one? And it basically describes the likelihood of a system failing at one specific time. So there it answers the question, if it's today, 3 o'clock, what is the probability that the cable will fail? And this is, of course, in reality, very hard to obtain, right? So this is more a bit theory now. But if we integrate over this function over the whole lifetime, then we get the cumulative distribution function. And that, of course, like approaches asymptotically the one at a certain level as well, because we have this assumption that every item or component or system will fail eventually at some point in time. And to come from the first function to the second function is relatively easy, because we just need to integrate over the first function. And and now if we continue this reasoning, and another concept can pop up. We can say, okay, when we cumulative over the failure probability over time, couldn't we also just switch this around? So instead of looking at the failure probability, we will look at the survival probability. And that's actually what is indicated by the survivor function here. So indicated with an R. And that's basically just 1 minus the cumulative distribution function. And now the last function we need to learn before we are ready to start is the failure rate function. And this is maybe a little bit more complex or a little bit less intuitive than the other three. But here the concept is, okay, if one component hasn't failed until today, what is the probability that it fail now? So there we take a conditional probability into account. And interestingly, this is the most relevant function, like mathematical function, because this is what we can observe in reality. Because this is when a failure happens, it it happened due to this, right? Because due to the condition that it hasn't failed before. And this linear behavior here of this function is of course only an example. So in reality, I will skip this. But in reality, it in most cases follows this so-called bathtub curve. And this is very famous in reliability theory because it describes a very typical failure behavior of many components, many systems. So at the beginning, when we install something, there the failure rate function is actually higher because we can have some problems in installation, we can have some material defects. Then it goes down, so it's in the useful life period where it never approaches zero because there can always be something. So that's how I look at it. But then at some certain point in time, it starts to increase again, and this is called then wear out time. And as you can see here, I think in my opinion, when I look at it, I find it very, very amazing, this slide, because you can see that this PLC behavior actually follows this exact wear out period from the theory, right? So we can see that it pretty much follows this functional behavior as often referred to in literature. But then from a mathematical point of view, if you're like not very practical, you could say, yeah, but I'm more interested in like, how can I model this behavior, right? How do I obtain this failure rate function? What do I need to do mathematically? And there, a very useful distribution comes into place, which probably a lot of you have also heard or used maybe during your studies, and it's called the Weibull distribution. And it's highly connected to this domain of reliability engineering and survival analysis because it's very flexible in modeling different types of this hazard rate or this failure rate function. It can be modeled increasing, decreasing. It has a exponential behavior, but it has more capabilities also if we compare it to the exponential function. Yes, and that's why also in a lot of previous literature, this function has been used, right? So the real data was collected, and based on this, the Weibull distribution was fitted to the data in order to model this failure rate function. And from the failure rate function, we can go back to all the other equations because they have a mathematical link. Yes, but this slide is just to point out, of course, this Weibull function is just one approach. In the literature, it offers much more approaches and also sometimes simpler approaches. For example, one very simple approach on the left-hand side is the Kaplan-Meier estimator. And the idea here is, and I also find it very smart in a way. It just says, okay, we do not care about a hazard function. So we say like, why should we model a function? We just basically look on what happened, and then we draw the survival function based on the observations. So this is very flexible, but it's of course also purely data driven. So if your data doesn't work, then this method also doesn't work. And it's ideally for descriptive survival analysis, right? So we say, let's have the observation, let's see how this is. But then I want to show some other extreme from the existing theory, and it's called Cox proportional hazard models. And there it says, it doesn't really make sense to have one function, like one hazard rate function for all of my components, because I make the assumptions that I have covariates, like some drivers which affect individual failure behavior, and I want to be able to expand and like draw many survival curves. And this is suitable for data sets which have complex relationships. And then, as shown here, this is also drawn based on the data I will present to you later. yeah, we can then also see differences in behavior or failure rate behavior of different components, in our case, cables. Quickly look at the time. Yeah, we're fine. Okay, so now we have a little bit of background in terms of what is out there, what methods are available, also from traditional system reliability theory. So now we could ask, yeah, okay, what of this has been really implemented in practice, right? So what is used by the DSOs. And interestingly, one concept which is rolled out by a regulator in the UK follows a slightly different approach. So instead of a viable function, here an exponential function is used to model or even an approximation of an exponential function is used to model the failure behavior, which then follows a similar approach, but is a little bit less detailed in terms of modeling to simplify things even further. And one thing I want to highlight from this approach, which is very interesting, so not only the probability of failure is taken into the picture, but also the consequence of failures, so that we combine it to a risk value and can draw risk matrices in the end. I decided to not go much more in detail into this method today, but it's just to the main message for you is that this is one of the mainly used methods currently today, and even if we compare it to the theory we just saw, it's relatively basic, right? So it even goes beyond the viable function modeling. Here, one very positive thing is that it addresses the individual component level. So these exponential functions are drawn for each individual level, but it also comes with some limitations, and it's also we will have time to discuss them later during this presentation. A second use case I prepared for you today is taking from the Netherlands, and this study, these survival models, and in particular this Cox hazard rate model I showed you 2 slides earlier, has been used for differentiating the aging of low voltage PLC cables. So it's the same technology stack. It's in the low voltage network, and they show that they actually can improve the asset management processes if they apply these methods, and if they differentiate different survival functions for each asset. And then we can see here on the right hand side, we can combine it again, similar to the model in CNAME model. We can combine it with some impacts, like the number of customers, for example, connected to the cable, and then we can hotspot cable networks with the highest risk, mark them red in this case, and then make our replacement strategy based on this. Okay, now we're coming to the key takeaways of this first part, and so the first key takeaway is the modernization of the distribution grid. This requires huge investment in the infrastructure. So this is a fact. Second takeaway is we need to have condition assessment, because otherwise we're having a hard time to prioritize and postpone our investments. When we look at all the components, we see that medium voltage cable networks are very relevant component to look at due to several system reliability indicators, but also due to different types of technology stages. We know that the aging factors of these cables are multifold, so they have complex mechanisms coming from thermal, electrical, chemical, and mechanical drivers. But at the same time, we also know this sustainability theory is the very well-defined research domain, which offers many methods and for this reliability monitoring. And we can also see that previous research has already shown that it's a useful tool to improve our rollout and investment planning. So here are some references for further reading. One core question is, okay, if we have traditional reliability methods and we have already applied them, and we also already see the positive benefits for asset management, why do we need to change, or why do we need to push for reliability models based on machine learning? And that's where I want to start this part of the presentation with. And first of all, I want to outline some of the limitations of the traditional methods we just looked at. And one strong problem with the presented methods is that they rely on a specific statistical assumption. For example, in the case of the Weibull function, we have the assumption that our failure behavior of the components follow this function. Or another downside is that we may, for example, in the Cox-Hazard proportional model, we make the assumption that the failure rates or feature contributions are constant over time. And all of these different limitations or issues, of course, there are also individual methods tackling these issues in particular, but you can summarize them in one core problem that these models can have a hard time in capturing the complexities of real-world data. And on top of that, they often, as we had in the discussion we had with Agrippina, for example, for the Kaplan-Meier model, these struggle in particular with large, unstructured and multidimensional data. And another problem is that it's difficult to apply these models in dynamic and fast-changing environments. And this is also one research question we have in our projects. How can we transform these reliability towards a more dynamic evaluation or prediction? And this comes us to the opportunities to integrate machine learning and AI into these models. Because AI, as probably you all in this room are aware of, they can actually learn patterns directly from the data. And what do I mean with this? They can create every existing function which is out there in the world. That's also already mathematically proven. They can model when they are fed with the right data. So this, of course, gives a lot of flexibility. And this can also then lead to the fact that they change from constant covariates to perfect. Okay, I just heard that people online couldn't hear me, so I will try to quickly recap some of the core. Yeah. Okay, 30 seconds, so then it's fine. Yeah, but to quickly summarize, so limitations of traditional reliability models is that they based on specific statistical assumptions, for example, constant failure rates or predefined failure distributions. And machine learning exactly offers this flexibility. So AI models, they can not only model one function, but they can model every function which is available in the world. So they basically just represent what is given from the data. And that also offers more flexibility in terms of what is the feature contribution over time. And another very important thing I want to point out is often we're talking from, okay, we are changing from traditional methods to now to AI and artificial intelligence, but this is of course not true because in research and academia, classical reliability techniques have been combined with machine learning and artificial intelligence, so that we also often end up in situations where we have ensembled methods. Of, for example, one example is the survival random forest, and that's also something we need to take into consideration. So for model development, so that we have actually two options. We can follow the pure machine learning data-driven approach, and then take all the advantages which are related to that. So very well established programming frameworks, a very broad range of tools and methods available. But we can also follow the approach of ensembled methods, where we actually combine certain machine learning techniques with the existing reliability techniques, which are then targeted to this specific use case. So, but how would it look like now on a very, very simple point of view to not follow the reliability approaches, but traditional machine learning approaches? Yeah, one example is given here by a very simple regression classifier. So we could take data from a DSO, sorry for that, we'll go back, of failed and non-failed components. That could be cable sections or cable systems. We balance the data set out with techniques such as SMOTE. For the ones who are not aware with this, so this is synthetic minority oversampling techniques. So we basically pre-process the data so we have a balanced data set. Then we can train a classification algorithm. In this case, it's a logistic regression model. Then we can use this trained model. We can load it in some applications we are using, for example, within our asset management software set. And then we can, in this case, it's applied on random values, but then we can use this model to make predictions in terms of the conditions. And then in order to also have a logic behind, in this case here, are then the individual cables ranked after their probability of failure. So that could then be an impact input for example, investment prioritization. Interesting in this approach is that this basic concept, it works, and it can also show feature contributions as indicated here on the left-hand side. But of course, this example is very basic, right? So we're looking only on two features, and it is also was trained on a limited training data set. So, and this already points out like the tasks we need to follow. So we need to work on the basic infrastructure for machine learning models if we want to follow this approach, which is the data. So we need to have feature-rich data sets. We need to have high-quality data, and then we can start exploring and reflecting on different methods. Because here the assumption of we're taking a logistic regression classifier is of course also to be questioned, right? So is this the ideal method to follow? This needs to be checked. Yes, and that's also what I want to focus on in the second part of this presentation, in terms of what are the actual implementation challenges we face if we follow this purely machine learning driven approach for reliability prediction. And as already mentioned, we can see that data collection, enrichment, and fusion, they represent a big part of the workload. And to put that into perspective, because when you hear now, okay, data collection, but what data collection are we even talking about? So as I mentioned in the introduction, so I'm based in Denmark, affiliated to Green Power Denmark. And Green Power Denmark represents the DSOs in Denmark, or is an interest organization for the DSOs in Denmark. And yeah, for this project, 5 DSOs in Denmark were willing to, or were kind to provide us with yeah, data from their assets. And in order to keep also the study in a manageable manner, we decided to request data from 5 DSOs, which is already very ambitious because this also comes with a lot of problems in terms of data combination, data fusion, which I will present to you later. But now, when you see the following slides and you see some white spots on the map in Denmark, that doesn't mean that there's no grid infrastructure installed there, but this just means that yeah, these DSOs in that areas haven't been part of our study. So we started with rethinking data requirements for the reliability assessment based on the aging drivers we saw earlier today in the morning. So we said, are there existing standards, existing literature, which define aging mechanisms, so which are relevant for the reliability prediction of medium voltage cables, and how can we extract features based on this? And we came up with a lot of different requirements. First of all, of course, we need to have knowledge and information about our components itself. Is it a PLC cable? Is it a PEX cable? Yeah, what is the core diameter? What is the number of cores? All of this can play an impact on the models, but also, and this is of course very relevant, like what is the installation date of the cable, so that we can calculate back what is the actual age in operation. But in order to be able to train our models, we of course also need data on historical cable failures, because otherwise, how can we make the correlation and also causality between the the failure event and the asset information. Then we have one category which is related to the cable location, also the cable placement, where we then can collect a lot of GIS-based features, which are related to climate information, but also road information, digging information, soil type, and so on and so on. And the last category is operational data, which is then reflected by how much is the cable loaded. But there we also faced challenges in terms of data availability, because yeah, the smart meter rollout, of course, enables us now to collect data of loading on an aggregated level, but it was not possible for all the DSOs. So we have collected loading information for certain DSOs, but not for all. Yeah, so how does it look like then after we have harmonized the data? So this slide maybe for you looks like not much, but for me actually it was very important, because here we see the data harmonized for all the DSOs. So that means we're not just showing some substation, but we're showing them with the same features and the same structure. This is actually requires a lot of work, but it's a very important fundamental for building the machine learning models, because otherwise, if we do not follow the same data and structure, yeah, we can basically only train individual models, and then even it's also hard to compare. So that was a strict requirement. Here it is visualized, yeah, certain component types we need to have information, or we require information in order to build the models. And of course, on the right-hand side, the medium voltage cables as a core asset for building our models. But of course, as mentioned, we need to do the same for the geographical features. So here I decided to only show two, how it looks like. On the left-hand side, one information are digging activities, which are actually tracked in a separate database in Denmark, but also very straightforward information such as road information were collected. Yes, and now I want to dive a little bit deeper into the next core part of the data requirements, and these are the medium voltage cable failures. And I think this is a very nice example to also show the challenges we have with the data which is available. So of course, we have challenges for the data I've presented here as well. For example, for asset data, there are features missing, or we need to harmonize the data. But also in particular for the failure data, because it's a database which has been installed over 40 years ago. Then we also face data quality issues. So a lot of highly relevant features, for example, where the failure happened, is not available in the data set, which of course poses challenges in terms of how can we connect it, how can we relate it to the GIS-based features we collected. And another problem is, as you can see here, I hope it's readable also for the people online, so that the installation date is only in 50% of the failure reports tracked. So that also comes from that the operational colleagues, maybe they do not know what the age of the cable was during the failure, or there are challenges in properly tracking it. So I don't want to go into details about the reasons, but this is then the reality we face while working with such data. But in order to increase, so now we have two different options. Obviously, we can either say, okay, all the data we don't have the information we disregard, but then we have a lot of data which is lost. And the question remains: do we have enough data to train our models on? Because machine learning, as we all are aware, requires a lot of data, so high amounts of data. But another option is that we can follow strategies to increase our information. And one thing I wanted to show here as an example is that if we combine the different data sets we've collected now, for example, the asset data and the failure database, then we can increase the amount of information available. For example, in this case, we have an old cable type. So this PLC insulation, it's like the orange line. And in a very small section, we have a modern cable, so a PEX cable. And this is, when we think about it, very unnatural behavior, right? Because why should we install a very small PEX section in a very long PLC cable? So, and this indicates that there has been a repairment section, or a repair has been done. So, and that can then be linked and be referred to a failure report, and can then provide the missing information, such as installation age or location of the failure. And we did that in one of our studies and showed that in this way we can increase the information available. And there are also different approaches we can follow. We can make it purely based on GIS information, but we can also define some rules. And another option is to make it on fuzzy mapping. But here is, of course, a trade-off necessary in terms of certainty about the mapping process and the amount of matches we can make by this. Okay, now maybe if we pause a bit. So now we know we defined the data requirements. We defined what data we need. We collected the data for all for the relevant areas in Denmark in terms of assets, failures, features, and we also investigated them in terms of data quality, and we came up with certain techniques to enrich the quality. But we still face the problem that it is very hard to manage the data. So when we want to train a model, we need to have it very structured in a clear output, in a clear table, which we can then input to our scalars and to our encoders. But if we purely do it with Python scripts, then it's very complicated and very messy. So that's why we decided in the project to propose a database structure. And because we are not, other than Lunozzo, we're not researching on new database types. We just followed a very traditional and well-established relational data model approach. And we have a lot of good reasons to do so. So first of all, we provide a structure to our data, which and we facilitate the calculation of certain attributes. For example, we can very easily count the number of subsections of a medium voltage cable system just based on the data connection. Or another thing is we can very easily aggregate the length of a radial in the network based on the underlying cable systems. Or we can so it just offers us a lot of flexibility in terms of how we pre-process and how we prepare the data. And it also reduces repetitions in the data processing. And another problem, and I hope that I will have convey the message very well for you. In this setting, we also do not know what input data will be the best, or what combination of different parameters and decision design choices, that's the right word, for building our model is the right one. So that's why we also need to have flexibility in extracting different training data in a very fast and easy manner to try out and investigate on these different model design choices. And this is also facilitated through this structure, through the creation of database views. And just to show you one example how it could be done now. So we just mentioned the medium voltage cable systems, so as our asset data, which we received. And we also named the digging activities as one feature for the cable placement. And with the database, then we can very easily just extract the GIS overlap or based on the digging activities and the cables. And this can then provide as one feature. And here is just visualized to see how it is. And it's also something which happens over time. But for preparing the input data for a reliability model, we would, of course, not only map the GIS information of digging and cables, but we map all the other features as well. And there the advantages occur. Yeah, and this is a very small excursus now, because yesterday in the afternoon we heard a presentation from Lunozzo on peer-to-peer and decentralized databases, and also the tutorial from Massimo and Lunozzo in the afternoon. And during discussions with Lunozzo, we realized that my application case of reliability modeling with data from different DSOs actually represent a very nice use case of this decentralized data storage. Because if we take now this proposed relational database model and roll it out on all the different DSOs infrastructure, then we could implement such a peer-to-peer overlay, and then we could not only facilitate the data combination from a central database, but directly take the data from the DSOs individually. And that would come with a lot of benefits in terms of data sharing across stakeholders, but also dynamic updates. Because in my case, for example, I collected the data beginning of my PhD, so 2 years ago, but now the data is already out or beginning to become outdated, right? So if such a process would be in place, then also the requests of actual data could be facilitated. And I thought it would be nice to just squeeze this slide in, that you can also see one of the links between the projects we have. So now I would, if there are no questions, and also looking at the clock, we have 20 minutes left before we hand over to Kutai's presentation. I would like the opportunity to dive into model development and benchmarking. So as already mentioned, we have a lot of design choices for building our reliability models for medium voltage cables. So because medium voltage cable is a network, right? So we have different hierarchy levels. So we can have target our model on an individual medium voltage section level, which is defined between 2 cable joints or 1 joint and a medium voltage substation. But we can also look on a cable system level, which then is defined between 1 substation and another. Or we can even go one level up and look at radials. So there is it's a decision to make, right? So which hierarchy level is the best to target for obtaining proper results for our reliability prediction. And there are a lot of other decision indicators. I can, for example, name the methods selection as one very, very obvious one, which needs to be made. Of course, we would like, in our project, we would like to explore multiple design choices as possible in order to indicate favorable ones. But we also would like to prioritize relevant design choices, right? So that we are not building or investigating something which is not in line with industry needs. And one problem I observed in academia, and I also wanted to highlight that to you guys today, is that often if someone proposes a new method, it cherry picks some of the things which are available, right? It, for example, let's look at the sections, and I select only a subset of features. I'm working with the data I have, and then I maybe select one of the methods which are available. I train this, and then I propose it as the only solution, right? But from or not the only solution, but as one very promising solution. But the issue with this is that it's often, of course, optimized to one data set and the available framework conditions, right? For example, if I'm a very strong and powerful DSO, I can propose a method which maybe is fine with because it has a lot of data to train. But when I'm a smaller DSO and I don't have much data, then the method is probably not applicable anymore. The same as maybe I have a DSO who has collected very well the age information in the past, but was very bad in terms of tracking some of the core material. That's maybe a bit like not the best example, but there are differences in strategies of data collection which lead to different framework conditions, and they should be reflected in a fair comparison. Because otherwise, if we now propose one option, then it will be difficult to reproduce for other DSOs, and it's also difficult to generalize conclusions, right? When we make a study and we have very nice data about the road network, for example, and then we make the conclusion, okay, it has a big impact on a cable reliability. But if we then take digging activities into the picture, and then these then maybe we need to make other conclusions. So that's why we also should target a situation where we actually can benchmark these different environment conditions in order to generalize conclusions. Yeah, because otherwise there is still the limited opportunity to understand the dynamics of the problem. And that also goes in hand with the theory you probably also are all aware of, that there is no one combination of design choices or one method with fits all the use cases, right? So we probably will also end up in a situation where certain methods are more relevant for certain data requirements and the other way around. And in our project, of course, we cannot investigate on all different environment conditions. Even for the 5 DSOs, it's challenging, but we can implement the benchmark environment, and that's what we did in the past. So we developed a pipeline where we can track the performance indicators based on different data set combination, based on different models. And we also created in a way that we can, in a very fast way, compare different design choices. And that can help us because then we can indicate what features, for example, are very relevant or what methods are favorable for certain data sets and not. And yeah, today probably we will not have time to go very much into detail into this benchmarking results. And also, to be honest, I'm still in the working process of gathering the results. But I wanted to highlight to you how it could look. For example, here we have now compared a lot of different classification methods. So a very relatively simple type of machine learning methods available. And we can see that one of them is outperforming the others, both for some, and we did it with a matrix called failure capture percentage. And we selected this method because it's also is possible to calculate this matrix for a lot of different approaches, because it's not always the case, as you can imagine, that so all the survival analysis models and the machine learning models have the same metrics as an output, right? So we also need to formulate a matrix which is actually comparable and which actually enables this benchmarking. But this of course leads us to the question, yeah, what adjustments do we need to do to actually make this performance better? So if we add a feature, if you transform a feature and this curve goes to the left, then we can be happy and we can also take this as a generalization if we run this for different predefined benchmark data sets. And yeah, that leads us to the outlook that we say we need to explore more of these design options. We need to improve also the data input in order to reach to a point where we say, okay, the machine learning models have a performance which is actually sufficient to be implemented in real application and distribution grid asset management. So to sum up the talk for today, so the key takeaways I want to share with you, compared to the traditional methods, machine learning has the possibility, the opportunity to learn all functions or model all functions available in the world based on the data input, which provides much more flexibility in terms of the reliability model for individual cables. But yeah, data is the bottleneck, so we need to know what data we should collect, how we should enrich, how we should combine it, and this represents actually the big part of the workload. We have collected this for the Danish case, but we also got aware of the challenges related to that in terms of missingness, and also in terms of data management. We provided solutions for data enrichment, data management as the one topic shown from Donozzo. And in order to speeden up this exploration of design choices, and we realized that there will be not one option which will fit all the cases. So we should reframe our research formulation and like what cases should we prioritize, what methods, and yeah, we can already indicate certain, of course, also general relevance, right? Because it will also be the case that certain features will be relevant for a lot of cases, for example, digging activities or age. And then eventually we can then reveal the positive or negative impacts on differences in model choices, data choices, which then will, in the long term, lead us to yeah, new tool set in distribution grid asset management. So here I have some references and further literatures developed during the project. I think now we can close with some Q&A.